Dear students, we'll continue. So in the previous class, we have discussed about output equation and choice of specific magnetic loading, choice of specific electric loading, main dimensions. Today we'll continue with short circuit ratio. So this is the important topic, short circuit ratio. So this has been asked many times. The short circuit ratio of a synchronous machine is defined as the ratio of field current required to produce rated voltage on open circuit to field current required to circulate rated current at short circuit. Once again I will repeat. The SCR, the short circuit ratio of a synchronous machine, is defined as the ratio of field current required to produce rated voltage on open circuit to the field current required to circulate rated current at the short circuit. Figure shows OCC and SCC of a synchronous machine. OCC, this is the OCC characteristics. OCC means open circuit characteristics. This is SCC. SCC means short circuit characteristics. Okay. So now here this horizontal axis, here it represents field current. Here in vertical axis, it represents per unit voltage and per unit current. So now, see, this is the OCC from here. This is the OCC. And this is the SCC. This is the SCC. Now considering the similar triangles, that is OBFS here, okay, and OCF naught. Both have a same angle. That's why they are both the triangles are similar. Now according to definition, SCR short circuit ratio SCR is written as OF naught divided by OFS. OF naught, this is the OF naught. This is the field current required to produce rated voltage. This is the field current produce rated voltage. You can see here, rated voltage. This is per unit voltage. Rated voltage on open circuit characteristics, on open circuit condition. Okay. OFS. So this is the OFS from here to here. From 0 to OFS. This is the field current required to produce rated current on short circuit ratio. Okay. Short circuit condition. Okay, this is short circuit characteristics. So now OF naught divided by OFS. Now this OF naught equal to CF naught. This OF naught equal to CF naught. What is that? CF naught. This divided by this ratio. This we can write because of similar triangle properties. This ratio by this total OFS ratio is equal to CF naught divided by BFS. This I have written. CF naught, okay. BSF is equal to, see this BSF. This BSF is nothing but this AF naught from here to here. So this AF naught here is written. So 1 upon CF naught, it has been brought down. Okay. AF naught by CF naught. So now SCR is equal to AF naught. What is the AF naught? This is the AF naught. Per unit voltage on open circuit. Per unit voltage on open circuit. Okay. This is the field current required to. This will represent from here to here. Per unit voltage on open circuit. From here to here. Okay. AF naught. Okay. Now CF naught. This is the CF naught. Corresponding per unit current on short circuit. Corresponding per unit current on short circuit. So during this is the field current OF naught. That time it will produce unit per unit voltage. Okay, for same field current, how much short circuit current will be there? So that is represented with CF naught. So that is the reason this one divided by per unit voltage on open circuit divided by corresponding to per unit current on short circuit. So this is voltage by current. This is represented by synchronous reactance excess. So usually short circuit ratio is 1 to 1.5 for salient pole hydrogenators, and for modern turbo alternators short circuit ratio may be 0.5 to 0.7. Now we'll see the effect of short circuit ratio on machine performance. Again, this is important topic. This has been asked many times. So first thing, voltage regulation. Okay. So because we have to select low value. There's a range. Okay. So either you may select lower value or you may select higher value. So now if you select lower value of SCR, okay, lower value of SCR means that the synchronous reactance has large values. Synchronous values has large values. If SCR is low, this has to be large. SCR has to be large. And synchronous machine with low SCR have poorer inherent voltage regulation. That is, voltage regulation is more. If excess is large, because SCR is low, excess is large, SCR is low, excess is large, voltage regulation is more. Voltage regulation is more. That is poorer voltage regulation. That means this is voltage regulation is more, poorer voltage regulation, poor voltage regulation. Okay. So machine with high value of SCR, so it will be having better voltage regulation. Okay. Next, coming to stability, a machine with low value of SCR and thus high value of excess has lower stability limit, as the maximum power output of a machine is inversely proportional to excess. So here see SCR. Okay. If this is the low, this must be high. If SCR is low, excess must be high. Then maximum power limit, this will decrease. Stability limit also decreases, because stability is sincere. This maximum power is given by EV by excess. If this is high, PM will decrease. The maximum power limit decreases. Then stability limit will decrease. Now coming to parallel operations. Now we know that all the machines will be connected in grid parallelly. The generators are connected in the grid parallelly. So machines with low value of SCR are also difficult to operate in parallel because of high value of excess, because it gives a small synchronizing power. Which is responsible for keeping the machines in synchronism. In parallel operation, generators are weakly held in synchronism. Units may lead to out of synchronism for small torque and voltage disturbances. See here SCR is equal to, we know that, 1 by XS. Okay, if you select low value of SCR, it means that, okay, low value of SCR, excess is large. Now synchronizing power PSY, okay, it is proportional to EV divided by XS sin delta. So now here you can see PSY is inversely proportional to XS. So now XS, okay, XS is large. So XS is large, means PSI will be less, PSY will be small. It means synchronizing power will be small. It means for any disturbances in the load, because load will be always changing. Sometimes all of a sudden load will come, sometimes load will be thrown off. During those disturbances, unit should not lose the synchronism. So that power is called synchronizing power. So if excess is small, then the PSI will be large and machines will be held with other systems strongly. Now coming to short circuit current, a small value of SCR indicates smaller value of current under short circuit condition, owing to the large value of synchronous reactance. So now if excess is large, SCR will be less. Short circuit ratio this. Okay. So now short circuit ratio is less, excess will be large. Then because of high excess, short circuit current will be low. So you can see here in the circuit, This is a voltage. XL plus XA, this is the reactance due to armature reaction, leakage reactance. Both will constitute synchronous reactance. Then short circuit current is given by Eg dash by Xs. If this Xs is large, ISC will be low. This Xs is large, okay. This ISC will be low. When this Xs will be large, if SCR is low, SCR is low, okay. But this is not a problem because short circuit currents can be limited, and the synchronous generators need not to be designed with low value of SCR. Low value of SCR. Okay, this may be the advantage by choosing small value of SCR. So you can limit the short circuit current. But in the previous cases, we have seen many disadvantages. Many disadvantages. So this can be overcome. Okay, high short circuit can be overcome by using current limiting techniques. So here you can go for higher value of SCR. So excess can be less. So when excess is less, other factor, better voltage regulation, and Pmax will be large, and synchronizing power will be large. Those will have better. Those will have better impact on the system. Now coming to self excitation. So now you can see here, this is the machine. Okay, this is the generator. Okay, this is long transmission line. Okay, this is the circuit breaker. This is also circuit breaker. This is the load. So here during the entire transmission line, it is represented with the inductance and capacitance. These are the virtual capacitors. These are the line inductance. Okay, that is natural inductance of transmission line. This is natural capacitance of transmission line. Virtual. This is between line to ground. Okay, so we are not now here. This is the synchronous reactance of generator. So current is flowing like this. Okay, so now when load is there, load current will flow here. So because of load current, the reactive power is absorbed in the all the inductance of the transmission line, and these are the virtual capacitance. They produce charging currents. Now to produce required amount of voltage here, we have to give the excitation current here. Excitation current. So now because of that excitation current, required amount of voltage is produced at the sending end and this at receiving end. Okay, now all of a sudden load is thrown, the circuit becomes open. Now what happens? Current will not flow through this load current will not flow through this inductance. Okay, then some current will flow. It is due to the capacitance. Charging currents will flow. These are connected throughout the transmission line. I told these are the virtual capacitance. It existing between line and ground, because line is a live part and ground in between air acts as a dielectric. So capacitance exists. So because of that, only charging currents are flowing now. Because of that Faraday effects, now receiving end voltage increases. Okay, now what happens? Now already what happens? These are the leading currents. These are the leading currents. So no leading currents are dominating. So now when leading current flows into the generator, what happens? The voltage becomes, terminal voltage becomes much higher. Terminal voltage becomes much higher. Already you have set the that excitation current also. So now in the inductive load is not there, inductive drops are not there. Because of high excitation current, the output voltage of generator will be very large. Okay, so now this charging currents is also flowing through this excess, also flow through the excess. The load current and charging currents are flowing through the excess. That is the synchronous reactance. If this is large, then inductive drops will be large. Because of that, you have to give the required amount of excitation current. If this is large, more excitation current has to be given. If this is small, excess is small, less excitation current has to be given. Okay, this much you remember. So now, machines feeding long transmission line should not be designed with small SCR. It means high value of excess, as this would lead to the large voltages on open circuit. Large voltages on open circuit produced by self-excitation owing to a large capacity currents drawn by the transmission lines. Self-excitation of generators may occur due to large capacity currents of long transmission line connected to the generator. When load is disconnected, which may cause severe overvoltage and consequently consequently damage electrical power equipments and insulators of the transmission lines. Now coming to length of air gap. So a large air gap offers large reluctance to the path of flux produced by the armature MMF and thus reduces effect of armature reaction. Machine with large air gap results in small excess and high SCR has the following advantages, such as, so when machine with large air gap has advantage. What are the advantage? Because excess is small. If excess is small, better voltage regulation, small value of inherent voltage regulation. Okay, voltage regulation should be minimum. It should be small. Then only it is called better regulation. Okay, so better regulation property. The next, high value of stability limit, because excess is less. High synchronous power, again excess is less here because of excess, low excess. And better cooling, because through air gap air circulates. And lower tooth pulsation loss and lower noise level. And smaller unbalanced magnetic pull. Now, the machine with large air gap results in small excess. This we know that high SCR has disadvantages. What are the disadvantages? The excess is small. Okay. So now feed MMF, larger value of feed MMF is required because air gap length is large. So large feed MMF is required to push the flux through the air gap. Okay. So when air gap increases, diameter of the machine will increase. The size will be larger. Larger the diameter, hence larger the size. Then magnetic leakage increases. Weight of copper, the higher the weight of copper in the field winding due to increased field MMF. Cost, size increases and hence increases in overall cost. Hence, length of the air gap must be selected considering the above factors. Now, how to calculate length of air gap? So here, armature ampere turns per pole required is found out by using this equation: 2.7 TPH IPH kW by P. TPH is the turns per phase, IPH is the phase current, kW is the winding factor, P is the number of poles. Now, no load field ampere turns per pole, ATF naught. No load field ampere turns, ATF naught, is equal to SCR, short circuit ratio, multiplied with ATA. Okay, this ATA we have calculated. Assume SCR. Okay, suitable value of SCR must be assumed. Okay, so using this we can find out ATF naught. And also we have ampere turns required for the air gap will be approximately equal to 70 to 80% of the no load. 70 to 80% of the load ampere turns required for air gap, that is called ATG, will be approximately equal to 70 to 80% of the no load ampere turns. Now ATG is equal to, here, feed ampere turns per pole. ATG is equal to 0.7 to 0.8 ATF naught, 70 to 80% of no load feed ampere turns. Okay, but we know this equation, but the air gap ampere turns ATG is calculated using this equation. Okay, 8 lakh BG kg LG, where BG is given as KF B average or psi B average. This is form factor. Okay, now air gap coefficient, this or air gap contraction factor Kg is may be taken as 1.12 to 1.18. Now this you know, okay, this ATG you have calculated using this equation, okay. So BG you know, KG you know, LG you can find out. So using equation 1, 2, 3, okay, LG is found out ATG by, see this LG here is found out, ATG here, rest this term you bring this side, okay, ATG by 8 lakh kg BG. What is ATG? 0.7 to 0.8 sum 80 F naught, 80 F naught divided by 8 lakh kg BG. What is F naught? F naught you can substitute SCR into ATA, 8 lakh BG kg, okay. So ATA can be calculated using this equation. Substitute here, assume SCR, kg BG, okay, find LG, length of air gap. This can be found out, okay. Now coming to armature design, okay, number of armature slot. What are the factors to be considered while selecting number of armature slots? So this is also important topic. It has been asked many times. So the following factors to be considered for the selection of slots. First thing, balanced winding. The number of armature slots must be such a number that a balanced winding is obtained. However, the use of unbalanced windings generates unbalanced voltages and lead to the overheating of rotor surface due to surface harmonics, excessive triple frequency currents flowing in the neutral. Okay, these are the drawbacks. If you don't use balanced winding, okay, what happens? It will generate unbalanced voltages and lead to overheating of rotor surface due to space harmonics and excessive triple frequency currents flow in the neutral because of unbalanced voltage. Again, due to unbalanced voltage to delta connected induction motor, when you give unbalanced voltage to delta connected induction motor, negative sequence components will flow, which will overheat the induction motor, and also circulating current will flow in if the other generators are running in parallel. So other generators in that RYB phase, it may be having some voltage, it may be balanced one. In unbalanced one, it may not be matching with other parallel generators. That time, current will flow from higher voltage to lower voltage. So circulating current will flow from generator to one generator to another generator. These are the disadvantages. So next, so that is the reason you should always select the number of slots so that you should get balanced winding. This is important factor. Okay. So next, coming to cost, a small number of slots leads to a slight saving because there are fewer coils to wind, form, insulate, and place into slots and connect. Okay. So small number of slots leads to slight saving because there are fewer coils to wind and to form, insulate, place into slots and connect. And hotspot temperature. When small number of slots results in bunching of conductors, because number of slots are less means, so whatever the conductors, okay, are there, you have to accommodate in those conductors. Then conductors per slot will increase. So that results in bunching of conductors, leaving a smaller space for the circulation of air in the slot. So this gives rise to high internal temperatures in the slots. Next, coming to leakage reactance. When number of slots are small, okay, number of slots are small, okay, leakage flux, leakage flux, leakage flux, and therefore leakage reactance is increased owing to conductors lying nearer each other. So conductors per slot increases. So conductors has to be laid nearer to each other. So leakage reactance increases. Leakage flux, leakage flux increases. Therefore leakage reactance also increases when you select number of slots small. Now coming to tooth pulse. The tooth ripples in the field form and consequent pulsation losses in the pole phase decreases. And if you select a large number of slots, okay, tooth ripples in the field form and the consequent pulsation losses in the pole phase decreases if large number of slots are used. Lesser the ripples means generated voltage is free, will be free from the ripples. Okay, lesser the ripples means generated voltage will be free from the ripples. Okay. Now flux density in the iron. So with large number of slots, greater the space taken by the insulation. So because of this, slot width has to be more. When slot width is more, the tooth widths become less. So now this results in narrower teeth, giving flux densities which may be beyond the acceptable limits. Okay. So now those are the factors to be considered while selecting the number of stator slots. Now there are some guiding factors for the choice of number of slots. Okay. The value of slot pitch Ys serve as a guide. So Ys slot pitch, it is pi d by Ss, should be less than or equal to 25 mm for low voltage machine. Should be less than or equal to 40 mm for 6 kV or lower voltage machine. Ys should be less than or equal to 60 mm for machines up to 15 kV. Ys is between 50 mm to 90 mm for large hydro generators. Okay. Now second guideline factor. For silent pole machine, the slots per pole per phase QS should be between 2 to 4. Usually it is 3. In case of turbo alternators, the number of slots per pole per phase, this QS, okay, should be from 7 to 9. Should be from 7 to 9. So then fourth guiding factor, the number of slots per pole per phase may also be taken as fractional number such as 3.5 because it reduces magnitude of higher harmonics in the EMF wave. And fifth guideline, the slot loading should not exceed 1500 ampere. Okay, these are the 5 guidelines for selecting the slots. Now coming to finding the turns per phase, this is the equation. Okay, this is a normal equation. Always we used to have this equation. So if A are the number of parallel paths per phase in the winding, then EPH is equal to 4.44 pi TPH by A F into KW. Therefore, TPH can be found out using this equation. So in this one, EPH is applied voltage across, that is output voltage across each phase. KW we know, A is number of parallel path, F is 50. Pi is calculated using this equation. Pi is equal to B average to L. Okay. Then to find out cross-sectional area of the conductor, the phase current given by IPH kVA into 10 raised to 3 divided by 3 pH. Okay, current in the conductors IZ is equal to IPH by A. Okay, so last time we have discussed. Okay, there are two parallel paths like this. Okay, here in parallel path conductors will be there, number of conductors will be there. Here number of conductors, here number of conductors. Okay, now this is IPH. This is IPH. Now this current is IZ. This current is IZ. This current is IZ. Okay. Now IZ is equal to IPH by number of parallel paths. IPH by number of parallel paths. So now there are a number of parallel paths. Okay. Now cross section area of the armature conductor AS is equal to IZ by delta S. So delta S is the current density in the stator conductors given as ampere per mm square, that is equal to 3 to 5 amps per mm square. Now coming to slot dimensions, the flux density in the teeth at no load should not be more than 1.7 to 1.8 Weber per meter square. Now flux density is given by flux by area, that is flux per pole. Now area is nothing but number of teeth under pole arc multiplied by Li, that is net iron length multiplied by WT, width of the tooth. So now width of the tooth multiplied with the number of teeth under pole arc and multiply with Li, this will give area of the total teeth under one pole. So this number of teeth under pole arc is given by, this is psi into SS by P. This is actually SS by P will give the number of teeth under pole. Okay, that number of slots under pole, nothing but number of teeth under pole. And actual number of teeth under pole, we have to multiply with psi, that is number of teeth under pole arc. Multiply with Li, multiply with WT. Now this minimum width of tooth WT minimum is equal to, so this substitute B should not be greater than 1.8. So here B you have to bring this side. Okay, WT you have to bring this side. W2 you have to bring this side. So now WT minimum is equal to 5 divided by psi into SS by P into Li into 1.8. I have substituted because 1.8 this is the maximum, so width becomes minimum. Below this we cannot go, that is the minimum width we can set, where minimum width occurs at the gap surface. So hence maximum permissible width of this slot is given by WS maximum. YS, this is the slot pitch. WT minimum, this is the minimum. Below this we cannot go. If again, okay, so because of this width of the slot becomes maximum. Okay, this is WS maximum equal to slot pitch minus width of the tooth minimum. Okay, once you find out width, height of the slot is found using this equation. HS should be less than or equal to 3 times WS max. HS should be 3 times WS max. Okay, in this above this equation, psi is usually 0.7. Now coming to stator core, the value of depth of core, okay, this is DC, can be calculated by assuming suitable value of BC. The value of flux density in the armature core BC of a silent pole machine lies between 1 to 1.2 Weber per meter square. So now here BC is equal to flux in the core and area of the core. Here area of the core also given by Li into DC. Net iron length multiply with depth of the core. So now equating, so now you take this here. Okay, so now here AC also written as, okay, then what, pi C by BC. Okay, pi C by BC. This pi C by BC is equal to pi C by BC. Then DC is equal to pi by 2. This flux in the core is half of the main flux. Pi by 2 Li by BC. Okay, this already we have many times discussed in the induction motor also. So outer diameter D naught is equal to D, this is the bore diameter, plus 2 times HS. What is this HS? Depth of the slot plus depth of the core. This will give the outer diameter of the stator. Okay. Now length of mean turn of armature LMT is equal to 2L. This is empirical formula. 2.52 plus 0.06 kV plus 0.2 Okay. Now once you find out LMT, you can find out resistance per phase of armature winding RS. That is rho LMTS by AS. Already we have found out cross sectional area, turns per phase. Now LMTS you can find out. So resistance per phase of armature winding can be found out.